So, okay. Good evening, all of you. My name is Anil Yadav, and I am here to take the tutorial on fundamentals of semiconductor devices. And so, today we will learn about the compound semiconductors. So, now, so in first of all, what are the compound semiconductors actually? So, just okay. Huh. So, okay, let me check when someone wants to join the meeting. So let us see. Start and admit. Okay. So let us see. So what are the compound semiconductors? And compound semiconductors are the semiconductors which are made up of more than one elements. So what we have seen till now is we are working on the silicon only. We have seen the MOSFET, silicon solar cells, and all these things. So silicon and germanium is the most of uh, is used most in the semiconductor devices. So and MOSFET is the building block of the whole electronics. Whatever gadgets that we are using these days are made up of silicon only. So the base is the silicon. Okay, so why silicon is so popular other than the germanium or oxide semiconductors like metal oxides, zinc oxide, gallium oxide, or these gallium oxide is the new semiconductor that is taking uh, up these days. So in silicon is used because whatever we have used in the MOSFETs, we have this is silicon n plus plus silicon or n plus silicon is there, and then we are growing silicon oxide SiO2. So at this interface decides the how charge transportation happens in the semiconductor devices, because at this interface we are applying, there is a gate at this junction, and here is a source and drain. So at this junction, this junction, this SiO2, this junction this junction is so pure which we cannot get in the other semiconductor devices. And it is very easy to grow silicon dioxide over silicon. Okay, so which is the main reason for for the silicon electronics. And another thing is silicon is thermally stable than the germanium. Germanium and silicon both are indirect bandgap semiconductors. Okay, so and but everything cannot be done with the silicon, as silicon is an indirect bandgap semiconductor. Okay, so for optical applications like where we need the light generation, we cannot use the silicon, because silicon cannot emit light because of the indirect band gap. So for that we are going towards the compound semiconductors are which are made up of more than one element from the periodic table. Okay, so in this one there are, okay, someone wants to join, let me check. Okay. Okay, now so in compound semiconductors there are different type of semiconductors like okay, first we can see there silicon is the fourth there are in the periodic table, there is in the fourth column, silicon lies in between the aluminum and nitride. In this column, there is a fifth column, fourth column in between the third and the fifth. So compound semiconductors are made up of the 3 and 5 and 2. There will be 2 and 6 will also be there. So compound semiconductors are made up of 2 and 6 and 3 and 5. Okay, so in this one, they can be binary semiconductors which are made up of two elements, ternary semiconductors which are made up of three elements, okay, and quaternary which are made up of the four elements from the periodic table. Okay, they can be these are binary compounds are like aluminum nitride. Okay, these are the aluminum nitride, aluminum phosphide, aluminum arsenide. Okay, these are kind of the binary semiconductors. One from this one, this third column, and another one is from the fifth column of the periodic table. Okay, so okay, and so another so there is combination 3 and 3 from here. So there can be 9, more than 9, I think. 3 multiplied, okay, these can be 9 semiconductors can be compound semiconductors can be made from these 9 element, these 6 elements. Okay, so aluminum nitride, so another one is gallium nitride, gallium phosphide, gallium arsenide, and then again this indium nitride, indium phosphide, and indium arsenide. These can be made from these 3 and 5 uh, columns. Okay, so why do we need these such kind of compound semiconductors? Because okay, so when we use the aluminum nitride is very wide band gap semiconductor. Okay, this is around 6.2 electron volt aluminum nitride. Why? Okay, yeah, and if we replace the aluminum with gallium nitride is around 3.2 or 3.4 electron volt. I don't remember that correctly, but as we go down in this in the periodic table, aluminum, gallium, indium, so the band gap will reduce. Okay, so why the band gap reduces is because in aluminum in aluminum, electrons are tightly packed. Electrons are very tightly bind in the aluminum. Okay, gallium has more size. The size of the gallium is more than that of the aluminum, and indium size of the indium atom is more than that of the gallium and aluminum. So when we go down the periodic table, the size increases. As the size increases, electrons are not that tightly bind. Okay, so electrons can so that's why the band gap reduces as we go down in this type of semiconductors. And the same thing happens in this side also. If aluminum nitride, aluminum phosphide, and aluminum arsenide, as we go from aluminum nitride to aluminum phosphide, the band gap reduces. Okay, so we can have different wide different type of different element different compound semiconductors with different band gaps, which can be used for various applications accordingly. So for this aluminum nitride and this gallium nitride, aluminum nitride and gallium nitride, these are mainly used for applications in power electronics. Okay, where large is the more is the band gap. Okay, wait. Okay, so more is the band gap, and so the breakdown, or we can say, as we have studied earlier, the breakdown, it does not break down that much easily. Okay, so we can apply a very high voltage if the band gap is higher, band gap is more, and there is very less leakage current in large band gap semiconductors. Okay, so this aluminum nitride is mainly used in the electronic applications for high power electronics. Okay, so we can tune the band gap in the compound semiconductors. That band gap tuning we will discuss how it is used in the ternary semiconductors. So we can mix these two, aluminum nitride and gallium nitride, aluminum arsenide and gallium arsenide. We can mix these two compound semiconductors to make the alloy of these, and we can tune the band gap. Okay, this is the band gap tuning. So, and the lattice constants, the aluminum nitride has different lattice constant than the aluminum gallium nitride. So uh, which gives us the different band gaps. Okay, the lattice constants gives us the, because of the different lattice constants we get the different band gaps of the semiconductors. Okay, and another thing is the flexibility to tune the devices. Because of the different band gaps of we can tune the band gap of the compound semiconductors. So we can tune the we can get the desired band gap for our applications. If we need a LED with the red emission, with the green emission, with the or with blue emission, we can tune that band gap accordingly to get the desired emission of the light from that from the device. Okay, from the LED. And okay, so now what other things that we can see is uh, okay, now we will see the alloying of these aluminum arsenide or gallium arsenide, whichever you want to take. There are different combinations: aluminum phosphide, gallium phosphide. We can do the alloying of these two. So okay, so now okay, here what we can see is okay. This is the one example I have shown. I am going to show you. So these are simple semiconductors or the elementary semiconductors that we can say. So this is the silicon and germanium. Okay, and compound semiconductors are made up of the 3 5 that I already told, and 2 and 6, 4 and 6. Which are given silicon carbide. This silicon carbide is used for high power electronics. Okay, and this mainly we are focusing on these 3 5 semiconductors, because these are widely used and gaining the momentum in electronic devices. Okay, so as we know, gallium is from the third column. So it has 3 electrons in the valency cell. Okay, this 1, 2, and 3. Okay, and arsenic from the fifth group of the fifth group. So it has 5 electrons in the valency cell. Okay, when we okay we make the compound semiconductor. What will happen is, okay, there is one gallium, one arsenide. They will be interconnected. They will be connected. One gallium will be connected with the 4 of the arsenic atoms. Okay, so like this. So it will be kind of a tetrahedral structure. Okay, gallium, there will be one more. Okay, this arsenic will be connected with the 4 gallium atoms. Okay, like silicon only, like silicon only. Okay, so so if the concentration of gallium is more in gallium arsenide, it will make a p-type semiconductor. Okay, more concentration of gallium in gallium arsenide will make p-type. More concentration of arsenic in gallium arsenide will make n-type semiconductor. So here directly we can tune the conductivity. Okay, we can tune the conductivity. We can make n-type or p-type semiconductors directly. But in while growing gallium arsenide on a substrate. Okay, well, this is not that much easy to grow a gallium arsenide on a wafer, on anything, on a substrate. It is a bit difficult, but directly we can get the n-type and p-type semiconductors from the gallium arsenide. But in silicon, what we do is we dope it with the boron to get the p-type semiconductor. We dope it with phosphorus or arsenic to dope it n-type semiconductor, to make it n-type semiconductor. Okay, we externally dope it. Okay, so now so this is the group 5, group 3, and group 5 we are focusing on. Okay, now so how okay, this is okay, from here what we can see, let us take the aluminum and nitrogen. Okay, this is the aluminum nitride which has the highest band gap. This is the band gap, this is the band gap of this is the graph of the band gap and the lattice parameters. Okay, so aluminum nitride, as aluminum and nitrogen are smallest in size, aluminum and nitrogen, we don't take the boron nitride as it is, boron is very high, very small in size. Okay, so we take aluminum and nitride, aluminum and nitrogen, so these are at the top in boron, aluminum, gallium, indium, and we take these three and these three. Okay, aluminum nitride is smallest in size. Okay, so the lattice parameters here, the lattice parameters are smallest. Okay, the whatever the structure, or whatever the structure it will form, BCC or anything, so it will take this the lattice parameter will be aluminum nitride. Okay, lattice parameter of aluminum nitride will be the smallest. So as we go in this the group, in this group, as we go down, the size of aluminum will size of the element will increase from aluminum to indium. Okay, so therefore the lattice parameter will also increase. Okay, so from in between 3 to 3.5, it was around, let us say it was 3.1. Now a is equal to 3.1, it was, now it is around 3.5. Okay, the lattice parameter has increased from aluminum nitride to indium nitride. So now, and also the band gap will reduce as the lattice parameter will increase, the band gap will reduce because it is indium. As I already told, the indium, the electrons are not that much tightly bind in the indium and indium nitride because of the large size. Okay, so there is a delocalization of the electron. More the delocalization of the electrons in the semiconductor, lesser will be the band gap. Okay, more is the delocalization. So you can refer to the previous classes, so that initial classes, that so more will be the delocalization, lesser will be the band gap. So gallium stands in between these aluminum nitride, aluminum and nitrogen, so there will be so the lattice parameter will be in between these two, and this is the this is the band gap of that, which is around 3.5, which is around 3.5 electron volts. Okay, now if we go, okay, the another thing is, so okay, this is the hexagonal, this is the cubic, these are the different structures of the aluminum nitride have will show different band gaps. Okay, so, and now what we will see is, in this one, the band gap tune, how we can tune the band gap of the semiconductor. So in the ternary semiconductors, that ternary semiconductors uh, are those when we okay, let us see if there is gallium arsenide and aluminum arsenide. Okay, aluminum arsenide, so these are gallium and aluminum are from the same group. So if we mix these two, alloying, we can say the alloy these two, so with, let us say with the 50-50% gallium, so it will form gallium, aluminum, gallium arsenide. Okay, aluminum gas, gallium arsenide. Okay, this is 0.5, this is 0.5, aluminum and gallium are 0.5 and 0.5, because we have made a 50-50 of a gallium arsenide and aluminum arsenide. So the band gap will lie somewhere in between gallium arsenide and aluminum arsenide. Okay, so aluminum arsenide will have the more band gap, which is around, I think, 2.2 electron volts. Okay, aluminum arsenide will have the more band gap because aluminum is smaller than the gallium. Okay, so it, gallium arsenide is around 1 point, I don't remember, I think 1.2 electron volts or 1.1 electron volt, I don't remember actually. Okay, so, and no, huh, I think someone wants to join, let me check once. Hello, Parth, do you have any question?
Sir, the screen was stuck.
Yes.
So we were not able to see the screen.
Currently, you are not able to see the screen.
No, now it's visible.
Okay, 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 okay. Uh, is it visible now? Hello.
Yes, sir.
Okay. Can you see whatever I am writing on the screen?
Yes, sir. Now it's visible.
Okay, okay, okay. So, when we alloy gallium arsenide and aluminum arsenide in some proportions, let us say in let okay, we can say uh, aluminium X, gallium is 1 minus X, and arsenide. Okay, so there will be proportion of X is to 1 minus X. Okay, so uh, we can tune the band gap of these two in between 1.2 to 2.2. I don't remember actually how much is the band gap of this gallium arsenide. Gallium arsenide I can check here. Actually, this one is for the nitride only. Okay, gallium arsenide. Gallium arsenide is here. It is around 1.5 only. It is around 1.5 only. Okay, so we can tune the band gap like this. Okay, so okay, I don't know. I don't know how to clear it. Okay. Okay, eraser. Okay. Huh. Now, so this is taken as aluminum nitride and the alloys of aluminum nitride and gallium nitride. If we take the alloy of aluminum nitride and gallium nitride, in between there will be aluminum gallium nitride. Okay, uh, so aluminum nitride has 6.2 around the electron volt of this band gap, and gallium nitride have around 3.5 electron volt. So aluminum gallium nitride, the composition, so we can tune the composition. We can say aluminum 0.1 and gallium 0.9 nitride. Okay, so have it will have near to the gallium nitride, because gallium composition is more. Okay, in this one, so the band gap will lie around here. So these are aluminum gallium nitride. These are used for high power application kind of electronic devices. Okay, because the band gap is much higher. Okay, the band gap is much higher for uh, these kind of semiconductors are used for high power applications. Okay, and so these semiconductors which lie in this one, in this region, which is indium aluminum nitride and indium okay, gallium indium nitride, indium gallium nitride or gallium indium nitride. These are in this region, which are used for the which can be used for LED applications, which emits in visible region. Okay, and photo detectors which detects the light in the visible region. We can tune the band gap so such that to make a very high sensitive photo detectors. We which is specific to the wavelength. Okay, we can so some of these are used, actually these are used for the laser applications also, because we can tune we can get a precise kind of band gap, a precise emission of the light. Okay, with the uh, band gap tuning. Okay, and so this region. Okay, this region which is below below this red, so which is indium gallium nitride or another indium gallium arsenide also, indium gallium arsenide, okay, which is this region indium gallium arsenide, which has the band gap is very less, okay, band gap is below 1 electron volt, so which is used to detect the light in the mid IR region, okay, in the IR region. So which is very and in another applications they are used for RF applications also, and for optical communication, for these fiber optics. These are kind of the semiconductors which are used for the different applications, and only these compound semiconductors can can give us that much flexibility of the band gap tuning, so that we can use for the different applications. Not the silicon, not the germanium, neither of the um, of the elemental semiconductors can give that much of the flexibility, because the band gap is the constant, but we need different band gaps, okay, we need semiconductor with different band gaps. So in there are some applications where we need in LEDs, that we will see in the subsequent slides. So in LEDs what we need, quantum effects, quantum or what to say, there is okay, quantum confinement effects, okay, so the particle in a box kind of thing, because so that there is more efficient more efficient what to say, recombination, okay, so there is an, so this kind of quantum well is there, okay, so this is the semiconductor corresponding to which it emit the light, okay, so this region is the this is the band gap of the semiconductor EC EV, this is EC, this is EV. So corresponding to this semiconductor, because the electrons will be confined in this region, holes will be confined in this region, so they will recombine, and they will recombine and emit the light, okay, so this can be only be possible with the compound semiconductors, this kind of structures, okay. Now, so the Wiggers law, what Wiggers law gives the parameters of the unit cell, okay, so let us say this A is the lattice parameter of here it is the aluminum arsenide, okay, so there are atoms of the aluminum arsenide, so whatever structure it forms, so zinc blende or cubic, hexagonal, whatever, so there are lattice parameters A, B and C, okay, so how these will be modified, these A, B and C will be modified with the mixing or with the alloying of aluminum arsenide and gallium arsenide, okay, so what is the composition of the aluminum arsenide, x times of the composition of the this lattice parameter of aluminum arsenide plus 1 minus x times of the lattice parameter of the gallium arsenide, okay, so this is the this will form aluminum gallium arsenide, okay, this is the lattice parameter for aluminum gallium arsenide, so this is x, this is 1, gallium is 1 minus x, aluminum AlX Ga 1 minus x arsenide, this is the lattice parameter, Ax is the lattice parameter for that that alloy, okay, aluminum gallium arsenide. So this Wiggers law will give us the lattice parameter for that alloy, ternary alloy, okay, and it also so there is this band gap tuning that we were talking about, this how this band gap can be we can how can we calculate the band gap of the alloy, so there, so this is the formula for the band gap of the aluminum x, gallium 1 minus x and arsenide 1 arsenide which is there. So here, okay, this is the aluminum arsenide, we can say arsenide. This is gallium arsenide. Okay, so this is so the band gap of the aluminum gallium arsenide will be x times of the band gap of aluminum arsenide, and 1 minus x times of the of gallium arsenide band gap of the and minus b into this. B is nothing that it is no what we can call it is the Bowing parameter, Bowing, Bowing parameter. Okay, and into x into 1 minus x, which is the composition. So what is the Bowing parameter is, so actually when it is aluminum nitride and indium nitride, and in between there is indium aluminum nitride, so it is not a straight line. Okay, this is not a straight line which is there in the in uh, in lattice parameters. Okay, okay, I haven't included that one. So in lattice parameters, so from aluminum nitride to indium nitride there will be a kind of a straight line. Okay, lattice parameter. So but there is a bowing of this curve, bowing of this curve. Okay, bowing of this curve with for the band gap. Okay, this is that B is the Bowing parameter. Okay, so the cell parameter a that we are saying, so this is the graph. So with the x, how it is behaving, so this is behaving a kind of a straight line only. Okay, so how when we change the lattice parameter, how it behaves, that cell parameter, that a, that lattice parameter, how that behaves is linearly with the composition. Okay, but it doesn't this band gap doesn't follow the straight line with the composition. Okay, now heterostructure. Yeah, heterostructures. Okay, now just give me a minute. Mhm. Okay, now in heterostructures, what are the heterostructures actually? In heterostructures, okay, so whatever we see, like if you can if there is indium gallium, okay, and plus there is this indium gallium and indium gallium arsenide, indium gallium arsenide, the structure is the heterostructure because there are two different type of semiconductors. Okay, if there is an interface between the two different type of semiconductors, this is a heterostructure. Okay, so there are two different semiconductors which are making an interface in between them. Okay, this is the heterostructure. Two or more semiconductors are there in a device which is known as the heterostructure. Okay, so now so heterostructure is not that easy in the elemental semiconductor because in the band gap of this indium gallium arsenide is different than the indium arsenide, not gallium actually, indium arsenide. Okay, indium arsenide, because indium gallium is not a semiconductor. Indium gallium forms lies in the same group. Okay, so in the same group, so indium gallium arsenide and indium arsenide, these are two different semiconductors which forms a heterostructure. Okay, so now so it is not that easy. There is no heterostructure with silicon. We can dope it n type or p type, but there is not a but the band gap of the semiconductor is constant throughout the device. Okay, that we have seen in the pn junction. Okay, so there is a bending in the band. Obviously there is bending when we join p type and n type semiconductors, but there is no uh, they, okay there is no two different type of the semiconductors. Okay, so we cannot call that p type and n type semiconductor interface as a heterostructure. For that we need to have two different type of the semiconductors. Okay, so uh, now okay, silicon and germanium, silicon plus germanium, we cannot make these to we cannot join these two that easily, because silicon, the lattice parameter of the silicon is different than the germanium. Okay, so there will be a lattice mismatch between the silicon and germanium. So there is so that interface, this interface is not that good. Okay, so there won't be a efficient charge transport over this layer, that if silicon germanium over silicon, this layer will not be that good. It will be strained, it will be cracked, or something like that. Okay, it will be cracked because silicon SI germanium has more size, so the lattice parameter of germanium, A of GE, will be more than uh, A of SI. Okay, so this will be more. So growing over that, so okay, in the next slide I will show you why it is more important, because the interface will be more strained. Okay, that will be cracked, that we do not want. We want crystalline germanium, crystalline silicon. Okay, crystalline, because which is there at in the crystalline form of the semiconductors, there is very good efficient charge transportation. Okay, so in epitaxial growth, okay, epitaxial growth is like I have given you that okay, this is gallium gallium arsenide. Okay, this is the gallium arsenide, and over that we want to grow another semiconductor which has a different band gap than the gallium arsenide. So what we can grow is indium gallium arsenide. We can grow indium gallium arsenide. These this whatever we are growing above that, that should be of the same family. Okay, like 3 5, that okay, 3 5 semiconductor, this is the same family. Okay, and this is the from the same family. Okay, so this should not be from the different family, which is 2 6. Okay, this should not be from the other family. This is one family, this is one family. 3 5 is one family, 2 6 is one family. Okay, so this should not be, the epitaxial growth cannot happen from this zinc selenide or zinc sulfide, whatever. ठीक है, zinc selenide is one from the 2 6 group, and zinc sulfide is another semiconductor from this 2 6. Okay, now we can grow indium gallium arsenide. So epitaxial growth is that so gallium arsenide will have some lattice. Okay, this is lattice of the gallium arsenide. Okay, so this has some lattice parameter A, let us say, and indium gallium arsenide will follow this lattice parameter. Whatever structure of the gallium arsenide, that indium gallium arsenide will follow that same structure, that which is this we call epitaxial growth. Okay, so this is growing gallium arsenide over indium gallium arsenide is not that easy, because it should be a layer by layer, atomic layer growth. One layer first, second layer, then the second layer, then third layer. This will be a layer by layer growth. Okay, so that we call the epitaxial growth. Okay, which follows the same structure that is below the uh, that is whatever substrate that we are using. Okay, now, so how this can be realized, this epitaxial growth can be realized. This epitaxial growth can be realized with different tools, or we can say instruments, which is one is the molecular beam epitaxy, MBE. Okay, another one is MOCVD. Okay, so this is molecular beam epitaxy. This is MOCVD, metal organic chemical vapor deposition. Okay, this is the metal organic compound, this indium CH3. Okay, this is the indium atom, and CH3, three groups of the CH3 methyl groups are attached to it. Okay, and trimethyl indium, we can call it trimethyl indium. And there are some other compounds like trimethyl aluminium, trimethyl arsenic. So there are different molecular compounds, okay, different organic compounds, which so indium will react. Okay, now, so there is, so so there will be a layer by layer growth. So okay, let us say this is substrate, or there is already grown indium. Okay, let us see, someone wants to join. Okay, okay, now, okay, what happened? Okay, huh. So, huh. So, so this the epitaxial growth. So there will be a layer by layer growth. Okay, so there will be two type of precursors will be there. We can call it, this is one precursor and this is another precursor, which will form indium. This is indium arsenide, actually, indium arsenide. And there, if there will be any other element we want to deposit indium gallium arsenide, so there will be one more precursor, gallium precursor will also be there in the in the in the chamber. So that will grow indium gallium arsenide. Okay, and in this case we have only two precursor, indium and arsenic precursor, so it will grow indium arsenide. Okay, now, so this is a setup kind of a pictorial, not a pictorial. This is a this is uh, a principal kind of. So here, this is the MOCVD. So how that MOCVD works, that I will tell you. So there are gases of the precursors. So whatever we want to deposit, so indium gallium arsenide or indium arsenide, gallium arsenide, whatever we want to deposit, so there will be a carrier gas and there are reactants. Okay, so carrier gas we can take is nitrogen, most of the time nitrogen, or nitrogen, or there may be another gas which is uh, non-reactive. Okay, so, so nitrogen is the carrier gas, and there are reactants, which organic metal organic compounds. Okay, metal organic compounds which are trimethyl aluminium, trimethyl indium kind of. ठीक है, TMA or TMIN, TMA and TMIN, and there may be ASH3. Okay, this is another material, and for arsenic. Okay, so arsenic will come from this side, and from ASH3, and aluminium and indium will come from TMA and TMIN. Okay, so there will be reaction. This is the carrier gas. There is a chamber. Okay, there is a chamber. So in that chamber we send these gases, and this is the substrate. This is the substrate that is there. So which can be aluminium arsenide. Let us say aluminium arsenide is there, uh, the substrate. So we want to grow aluminium in indium aluminium arsenide. Okay, so we can grow that with these two with these two reactants, with the carrier gas, and ASH3 will be there. So there will be a, this is the gas phase of the reactant, so that will go to the surface, there will be surface diffusion. Okay, that will go to the surface, it will react with the surface. Okay, it will react with the surface, and many of these come together and will form a layer. Okay, so this is the nucleation. Okay, nucleation, it will come, and next step is there is a growth. So this may be indium arsenide or aluminum arsenide, and the next layer can be uh, opposite to that. Okay, indium, aluminum, so there will be indium and aluminum in this growth. So, and another thing, after the reaction of this TMA with the substrate or with the layer, so this is the active layer. Okay, whatever the other compound will react to this layer. Okay, so there will be a layer by layer growth. So this aluminum or indium, okay, so after the reaction of this TMA and TMIN, there will be there will be products. So the products will dissolve. These are the volatile products, and they will go out with the carrier gas. Okay, they will go out, that this is the main gas flowing, that they will go out. There is an outlet of the chamber, there is an inlet of the chamber. Okay, so they will go of the out of the chamber. Okay, so here you can see there is a reaction between, this is the indium, TMIN, trimethyl indium, and there is a phosgene gas, phosgene PH3. Okay, so this TMA will react, TMIN will react with the substrate, or the previous uh, layered material, and it will react, and there will be byproducts. Okay, this methane will be the byproduct. Okay, this methane will go out with the this main gas flow. Okay, this will go out. So uh, and uh, and we can incorporate here only. So if instead of TMIN, we can send two gases, TMIN and aluminum arsenide, TMAS, no, TMLA, trimethyl aluminum. This is trimethyl indium, trimethyl aluminum. If we send these, these are the volatile organic compounds. Okay, when they react as soon as they go inside the chamber, they react with the layer. Actually, we are giving a temperature also. This is heated, so they react at the high temperature with the substrate. Okay, so and they are site specific also. They are okay, if this material, this okay, this is the phosgene, this phosgene will not react with the another material, another compound of the phosgene. So this will form a monolayer only, this will form a monolayer only, and then only it will react. So if this phosgene will react, so there will be more phosgene react, so it, so there, this won't be that good composition won't be that good. Okay, so we can change even the composition of the elements in this reaction, in this chamber, by sending by changing the partial pressure of the or the flow of the gases. If we are giving 5 SCCM or 10 SCCM, the concentration of the material will be will can be changed accordingly, and we can change the composition of the of that aluminum arsenic, okay, in this one indium, aluminium, indium arsenide. So here we can change the aluminium, indium composition by changing the partial pressure or the flow of the gas. Okay, so what we were talking about, so when we grow the these compounds, okay, so there is, so okay, this is the substrate, let us say that is indium arsenide. Okay, so indium arsenide, and this is the, let us say we are growing gallium arsenide. Okay, so so if the gallium arsenide and indium arsenide will have the same lattice parameters. Let us say, let us suppose they are not same, but let us suppose they are same. Okay, let us, the A is same for both. Okay, so then this there is no lattice mismatch between between the two, layer that we are want to grow and the substrate is that. So the lattice parameters are different. Okay, so because of the size of the elements. Okay, if the lattice parameters are same, then there won't be any strain in between these two layers, this layer and this layer. Okay, so in between the substrate and the growing first layer, there won't be any strain or stress in the layer. So if there is stress or strain, then the, okay, that we will see in this one. So this, if the lattice parameter A is higher that we want to grow than that of the substrate, lattice parameter of the material that we want to grow, epitaxial layer that we want to grow over the substrate, if that lattice parameter is more, so there will be a when these two will wants to, so when there will be a growth of this material, so it is feeling a force, inward force between these two. Okay, because the lattice parameter is more, so now it will feel a inward force because of to match this lattice. Okay, it will feel an inward force. Okay, so that will change the band at this interface. Okay, that will change that, because of the stress, the so the potential will vary, that and the cracks may happen in the film. Okay, so after some time, so after 3 4 atomic layers, this layer, 4 5 atomic layers, uh, this will be relaxed. Okay, this will be relaxed because it will go widen a little bit of widen, and after some of 4 5 atomic layers, this will be relaxed. Okay, and this will be like this only, this will be like this only. Okay, and in okay, in another thing, another one. So okay, this is this kind of, so the first layer, because of the lattice mismatch, so it is not it, so there it is not connected. This is this atom, atom is unbound, this atom is again unbound. So this is the lattice mismatch, because of the lattice mismatch, because the lattice parameter of the, or the a lattice parameter of this growth material is more than that of the substrate. Okay, so because of that, these are unbound. Okay, and this layer, other than the first layer, which we first layer, atomic layer, so these are unstrained. Okay, there is no strain in between them. Okay, so but if we want to grow very thin layer of this material, very thin layer, like 2 3 nanometers, 1 2 nanometers, so the crack, there might be some cracks in the film because of the lattice mismatch. Okay, and there may be grain boundaries because of that. This may be a grain boundaries because of this lattice mismatch. So uh, these things are not good for the for the devices, because because of these grain boundaries, there will be traps. Okay, they will trap the electrons or holes while transportation of the charge transportation. Okay, now, okay, now what I can see, if there is something more. Hmm. and these lattice structures, these are very important. So these are very important. Why these are very important? Because we need to make some quantum well kind of structures, or Okay, this I will tell you about after this, uh, after these heterojunctions. Okay, okay. Now, heterojunctions are come when there are two different type of materials, two different type of semiconductors come. We join the two different type of semiconductors. Okay, this is one semiconductor one. This is semiconductor two. Okay, so these two have different energy EGs. Okay, band gaps, EG1 and EG2. Okay, these two have different energy band gaps, and also uh, electron affinity of these two, the difference between the conduction band and the vacuum level, both these two are different. Okay, and the difference between these two electron affinities, which is EC1 minus EC2, if we say this is delta EC, this delta EC is nothing but this is known as conduction band offset. Okay, conduction band offset. Okay, so this delta EC is the conduction band offset. Okay, and this is the Fermi level of the first one, this red one. This is the Fermi level of the second one. When we when we uh, when we join these two, how these the bands will bend. Okay, how the bands will bend in a semiconductor in at the interface. This is the heterojunctions. Okay, so there are three types of the heterojunction: type 1, type 2, and type 3. So in type 1, so if the in type 1, if the band gap of the semiconductor 1, okay, this is the semiconductor 1, this is the band gap of the semiconductor 1 is more than the band gap of the semiconductor 2, and this is for condition 1. Condition 1, first condition is EG should be more than that of the EG1 is should be more than that of the EG2. And another thing is this uh, the band EC. Okay, this electron affinity should be more than electron affinity of second EG of the second semiconductor conductor should be more than that of the first semiconductor. Okay, so this is so what will happen is, so this will lie in a and electron affinity as well as the ionization energy. Okay, so these are such that the conduction band and the valency band should lie in between the in a conduction band and valency band of the another semiconductor. This is the thing. So so this will form a type 1 kind of heterostructure. So this type of if the conduction band the if the conduction band of one semiconductor of semiconductor 2 lies in between the conduction band and valency band of the second semiconductor of the, let us say, the first semiconductor, and this valency band or the say the ionization energy of the second semiconductor should be more than that of the ionization energy of the first semiconductor. Okay, so this will form a type 2 heterojunction. Okay, and the next type 3 is if the if the this electron affinity, this is the electron affinity of the second semiconductor is more than that of the ionization energy of the first semiconductor. This is the ionization energy of the first semiconductor, this is the electron affinity of the second semiconductor. So if it is more, then it will form a type 3 type 3 heterojunction. Okay, that we will see. So let us say aluminum gallium arsenide and indium aluminum arsenide, these kind of if when we grow epitaxial growth, we do the growth at the epitaxial growth, so we can form these several kind of the heterostructures or heterojunctions. Okay, so now so okay now So what will happen in this one? This is a type 1 semiconductor. What will happen? This is the conduction band, this is the valency band of the, this is the conduction band of the first semiconductor, this is the conduction band of the second semiconductor, and this will look like this. Okay, this is a type 1 semiconductor, and in this one what will happen, there will be a step, okay. So the band gap of this one is different, then band gap of this one is different. I am just showing you. So and so this if it will form the type 2 heterojunction, will be a step kind of the of heterojunction, okay. And this is the another one which is completely offset, okay, which is completely offset of the semiconductor, and this will form, a like this is the type 3 kind of the heterojunction, okay. Okay, let me check if card, okay. Okay, now uh, let us take one example of the type 1 semiconductor, okay. Type, if this type 1 heterojunction, so this is a n type semiconductor which has very less band gap. Then this is the p type, this is p type semiconductor. Actually this is n type semiconductor, this is p, this is n, and this is wide band gap semiconductor. Eg2 is greater than Eg1, okay. So in this one and this the electron affinity of this first semiconductor, semiconductor 1 S1 is greater than that of the electron affinity, which is Qi2 is more, than that of this type or second semiconductor, okay. And another thing is, so now when we join these two semiconductors together, okay, this is semiconductor 1, this is semiconductor 2, what will happen? So first, as we have discussed previously, the rules will be the same when we join two semiconductor, when we join a metal or semiconductor, when we join p type semiconductor with the n type semiconductor with this same homo semiconductor or hetero semiconductor, okay. If it is a homojunction or a heterojunction, homojunction is that uh, when we join p type semiconductor with the n type semiconductor, because the semiconductors are same, this is the homojunction. But heterojunction is such when we join uh, different semiconductors of with different band gaps, okay. So one is semiconductor 1 with band gap Eg1, and another semiconductor is the semiconductor with Eg2, and this conduction band and valency band lies in between of the first semiconductor, lies in between the conduction band and valency band of the second semiconductor, okay. So okay, so this will form a type 1 heterojunction, okay. Type 1 heterojunction, as we have seen, if this is the type 1 heterojunction, if one semiconductor conduction band and valency band of the one semiconductor lies in between the conduction band and valency band of the another semiconductor, okay. So this is the type 1 kind of heterojunction, okay. So first rule is, whenever we join these two, first rule is whenever we join these two, the Fermi levels should align, Fermi levels should be constant, and accordingly this vacuum level will go, accordingly this conduction band and valency band will go, okay. So the conduction band, this Fermi level is constant in this one, okay. This is EF1, this side is the EF1, this is the EF2, and when we join it will be common, and which is EF, okay. So so this is a bit highly doped, as EF1 is more closer to the valency band, and EF2 is less closer than the EF1 to the conduction band, okay. So this is N type, this is P type, okay. This is more doped, this is less doped. So so bands will bend at the interface accordingly. If the more is the doping, lesser will be the band bending, will be the lesser will be the width, depletion region width. Okay, more is the doping, lesser will be the depletion region width. Okay, so the depletion region width on this side will be lesser than that of the depletion region width on this side. Okay, so now, so when we join these two, the Fermi level should be constant. Okay, that we have seen. So, and another thing, another rule, next rule is this: these point won't move. Okay, these point won't move. This point will be at the same level, and this point will be at the same level. Okay, so okay, now okay, now what will happen is this wall semiconductor, the bands will move up, these will move down. Okay, so by transferring the electrons from here, electrons from semiconductor 2 to the semiconductor 1, and by transferring holes from this semiconductor to this. Okay, so these bands will align accordingly to make the Fermi level constant throughout the semiconductor. Okay, throughout the junction or semiconductor to the to compound semiconductor. Okay, or heterostructure. Now these points will won't move. Okay, and also in this region, so there won't be any effect. Okay, so the difference between these Fermi level and the conduction band will be the same. Okay, so when we move, this move will move down, this we have moved down, and by keeping this point constant, and this will move up by keeping these 2 points constant. First we will see at the conduction band only. So this is moving up, so this we will move up by keeping this point constant. This we are moving down by keeping this point constant. Okay, and the difference between these two at far away from the junction will be the same as it was before. Okay, so so the gap delta ec, this is the delta ec that will be same in the after the junction also. This is the conduction band offset. Okay, and also this conduction band and valence this valency band will follow the conduction band. Okay, this valency band in this side will follow the exactly same as the conduction band. Okay, now, and this valency band of the second semiconductor will follow the conduction band of the same second semiconductor. So this is the junction. Okay, so there was a gap. This is the delta ev, this is the delta ec. Okay, this is the delta ec. So this is the valency band offset, then this is the conduction band offset. Let me check someone is there. Okay, now admit. Okay, now uh, Sharwanti, can you turn off your mic, or if you have question you can ask directly. Okay, thank you. Now, so okay, so now so this whole part, as we have seen, this whole part will move up and this whole part will move down to align the Fermi level. Okay, the Fermi level will be constant after the after joining these two semiconductors. Okay, this is kind of a type 1 semiconductor. So as first thing I told you that this is highly doped highly doped p type semiconductor. The doping is more in this case than the doping in this n type semiconductor. Okay, this is n type semiconductor. As we can see, this ef2 is more closer to the ec2. Okay, or the conduction band, near to the conduction band. So the gap, this gap is lesser than this gap, so we can say that this is more doped, highly doped. So accordingly the bending happens at the junction. So the band bending at in this side of the semiconductor, first semiconductor side will be lesser. Okay, this bending 5 5p we can say, because this is the 5p. 5p is the difference between the this conduction band at the deep down in the in the bulk and at the interface. Okay, this is the 5p, and this is the 5n. Okay, this is nothing but 5n. Okay, so these are the two. So so the band bending at this interface is lesser, so that is because of the more doping in the p side. Okay, and another thing I wanted to tell you is, okay, so this is ec2. huh. hmm. Okay, let us see the next example now. So and another now what we can see, another thing what we can say is, so there is a kind of triangular this okay this is a, so electrons, so in this case there are more electrons than the holes. So actually okay, that will come in the next slide actually. So what I wanted to tell you is, if this conduction band is more below the Fermi level, then there will be excess of the electrons at this junction. Okay, so this is kind of a triangular well, we can say. This is already a triangular well, so the already the electrons are here. There are more electrons here than the bulk. Okay, so but there are these are lesser than that of the holes, because that still there is a more this Fermi level is more closer to the valency band. Okay, so now let us see in the example 2. So here it will be more clearer. Okay, and now here what we can calculate is the built-in potential. So okay, one thing what I wanted to tell you is this thing. So the vacuum level, so the difference is between this will always be continuous. There won't be any discontinuity in the vacuum level. Okay, so if there is discontinuity in the vacuum level, then the energy of the electron is kind of the infinite at that point, because if so that we have already discussed when we were discussing about the metal semiconductor junction. Okay, there when we were discussing about the Schottky junction, so there cannot be any discontinuity in the vacuum level, as the discontinuity in is there, as discontinuity is there in the conduction band and the valency band. So that discontinuity cannot be there in the vacuum level. Okay, so this is the built-in potential VBI here, not this one. Okay, not this one. This is not the built-in potential, not neither this one. Okay, so what is this thing? So this is phi n, this is phi p. So this VBI is equal to phi n plus phi p, that we will calculate now. So how can we calculate the built-in potential in a hydrostructure? Okay, so now okay, so I will show you one real life examples of the heterojunctions, that uh, the devices which are used in the devices which we use daily. So this is the aluminum N type of aluminum gallium arsenide. This is N type of gallium arsenide. Okay, gallium arsenide will have the band gap of the gallium arsenide will have lower band gap. Gallium arsenide will have lower band gap. This is the gallium arsenide, this is the aluminum gallium arsenide. Okay, both are N type. Now how it will so how when we join them, how the band bending will happen at the junction. Okay, so in this case, so Fermi level is higher at this point and this one, so electrons will move from the this first semiconductor to the second semiconductor. Okay, from aluminum gallium arsenide, electrons will move from aluminum gallium arsenide to the gallium arsenide. Okay, to align the Fermi level. So the Fermi level will be aligned first. Then the fix these 2 points conduction bands, and bend the bends accordingly. Okay, so it will move up, it will move down. Okay, so what how it will move up is, that will move, how the extent of the bending is defined by the doping of the semiconductors. Okay, how highly doped or moderately doped or lightly doped these two semiconductors are, so accordingly the bending will be there. Okay, so the bands will will bend like this. So this is the bending at the interface of the n type of aluminum gallium arsenide and n type of the gallium arsenide. So at this junction this is the thing what I wanted to tell you is, so at this point the Fermi level is above the conduction band. So there will be, so at any temperature we can find the electrons at this junction at any temperature, because Fermi level is such is the level. So at 0 Kelvin all the states are filled at below that. Okay, below Fermi level all the states are filled at 0 Kelvin. Okay, so we can this finding an electron at this point is the 100% probable. Okay, there is a 100% probability of finding an electron at this junction. So these type of devices can work at our lower temperatures, and they will work at better at lower temperatures, because there won't be any freeze out in this case. Okay, freeze out happens and in silicon, where there is no electron gas, the bands not does not bend like this. Okay, so in this case we can there will be a very good conduction, or the mobility will be higher at the lower temperatures. Okay, and there is another case which is like this, so which is n type and p type. So in n type and p type so the Fermi levels will align like this. Okay, so Fermi so this whole thing, this whole bands will move down and these whole bands will move up. Okay, by keeping these points constant at fixed, these 2 points fixed, so bands will move accordingly. Okay, so in this case there is a p type, so the band so the difference, there will be a very high bending at this interface because of the p type. Okay, and another thing is, this is the different another case. So you can draw the bend diagram easily of any type of the heterostructure if you know the basic rules. The two basic rules: first, align the Fermi level; second, fix these 2 points at the conduction band 2 points. Okay, just fix these 2 points and you are done. Okay, you are done. Now okay, so I don't find this is a mistake, I guess, because if we fix these 2 points there should be any some difference, because okay, it should go like this only. So there should be some difference, that delta EC should be there, which is not shown. Okay, this should be there, this should be a straight line, vertical line here at this junction. Okay, delta EC that much. Okay, so that should be there. So now what okay, this is a type 1 semiconductors only, type 1 heterojunction only. So now okay, just wait for a minute, discard. Now okay, now what we can see is, now what we will calculate the built-in potential that was there. So this is the built-in potential. Okay, this is the built-in potential VBI. So VBI is equal to phi n plus phi p. So what is the phi n and phi p is the band bending at the interface in the or phi n or phi p cannot be there. Phi 1 and phi p we can say. Okay, the band bending on the semiconductor one side and band bending on the semiconductor two side. So phi n and phi p I am saying because this is the p type semiconductor, this is the n type semiconductor. So for this there is a phi p. So this difference, the difference, this is the phi p and this is the phi n, another one is the phi n. Okay, so now what we can see is okay, so how we can calculate this thing is okay, the built-in potential VBI first we will see see okay, let us say this is the what is the this is the gap between this EC minus EG. So let us do some mathematics to for the energies of the band. Okay, let us do. So EC minus this EF, ECA, ECA minus EF. Okay, this is the this difference. Okay, this is this difference which is uh, psi a, you can say psi a. Okay, and that can be calculated easily because of the doping parameters. EC minus EF can be calculated easily because we know how much our semiconductor is doped. Okay, and EC minus EA EF plus this one, this is nothing but this is an n type semiconductor, this is phi n. Okay, this is phi n. Okay, now okay, now I think I have calculated that thing. Just give me a minute. Yes, EF. Okay, this is phi n. This is phi n. Then we have gone from here to there, this point. Now we want to come back. So how, what is this? This thing is nothing but delta EC. Okay, this is delta EC. Okay, plus delta EC minus plus phi n. Now we are going down in this direction. Okay, go down, so minus delta EC. Okay, this is minus delta EC. Now so this is delta EC. So now we are going up in this direction because this is nothing but this is phi p only. This is phi p, the band bending at the interface to the bulk, the difference between the extent of band bending, we can say the extent of band bending on the p side is this is phi p. Okay, we are going up, so in whatever we are going up in the up direction in the energy, so we are adding that phi p. Okay, this is phi p, and now from this we can go down till here at this junction or to the valency band. So we are going down, so this is the minus band gap Eg of that B, this material, the second material. And now so this difference, what is this difference? This difference is was psi n. Okay, this psi p, this is p type semiconductor, right? Yeah, this is p type semiconductor, this is psi p. So psi p is what is psi p is this is EF minus EV. Okay, minus, now we are going up. Okay, plus EF minus EV of B material. Okay, now this is the difference. We came back to this position. Okay, we came back to this position from where, so the difference between, so this must be equal to 0. The energies that we go from here to there and then come back from one side to the other side, so the it is at the same level. We came at the same Fermi level by adding and subtracting the differences in the energies. Okay, differences between the conduction band and all. So there are some terms that we do not know, this phi n plus phi p that we are interested in. So this is the built-in potential. This is the built-in potential. So just keeping these two one side, phi n plus phi p, let us send these on the other side, okay, which is minus of EC minus EF of EC of A minus EF, okay, okay, plus delta EC. This is the nothing, this delta EC is nothing, but this is the difference between the electron affinities q xi1 and q xi2. Okay, these are the different, this is the difference between the electron affinities. Okay, and plus Eg of the B material. Okay, and plus EF minus EV of B. So this can be calculated easily. So we know phi n and phi p. Oh, we know these terms. So EC minus EF minus EF is nothing but this is equal to KT by Q into ln of NC. This is the N type semiconductor, NC divided by ND actually, donor. Okay, this is N type semiconductor. So from here we can calculate the difference between these two. Okay, the difference between these two, and from here, so this difference can be calculated as KT by Q into ln of NV divided by NA. Okay, this is the doping concentration, Na is the doping concentration, and this is the effective density of the states, okay, of this material. So from here we can calculate this built-in potential. Okay, so it is not a big deal to calculate that thing. Okay, so now what else is, okay, now we can come on the graded heterojunction. So this is the kind of a semiconductor which has an abrupt junction. Okay, this is the abrupt junction, the conduction band and of the first one and the second one, they are there is an abrupt change in the conduction band. Okay, this is the abrupt junction. Okay, now what we can say is the graded junction. So if what is the, okay, let's check if how okay, let us say there is a material, semiconductor material, gallium arsenide, and another one is the aluminum arsenide. As we know, gallium arsenide has a lower band gap and aluminum arsenide has a higher band gap. Okay, so in between them there is aluminium gallium arsenide, aluminium X, gallium 1 minus X, and arsenide. Okay, so the band gap between of this aluminium gallium arsenide will lie in between these two, gallium arsenide and aluminium arsenide. Okay, so gallium arsenide have the band gap of 1.4 electron volt. Okay, 1.4 electron volt, and aluminium arsenide has 2.2 electron volts. Okay, this has 2.2 electron volts. So this is 1.4 electron volt, this is 2.2 electron volt. Okay, so this aluminium gallium arsenide will have the band gap in between these two. So what if rather than keeping this aluminium gallium arsenide at a constant this composition, if what if we gradually change the composition of this aluminum of gallium, of aluminium and gallium in this compound, aluminium gallium arsenide. Okay, if we gradually change the composition of aluminum gallium arsenide, so the band gap will change gradually. So this is the band gap. So gallium arsenide, if we increase the concentration of aluminum in this one, if we can increase the concentration gradually in gallium arsenide, so the band gap will change gradually. Okay, the band gap will change gradually till whole aluminum is there. Okay, so this gradual change, the slope of this depends on the on how we are gradually changing the concentration of aluminium in aluminium gallium arsenide. Okay, so that so this is nothing. This slope is because of that. Uh, okay, no, that is the field actually. So this slope is because of the concentration, that change in concentration of aluminium. Okay, and what another thing is, I wanted to tell is. mm, so okay, now what initially what we had is this gallium arsenide. Okay, there is this wafer of gallium arsenide. Now we want to grow aluminium gallium arsenide. We want to make it graded junction. Okay, graded heterojunction. So how we will do that is, we can in MOCVD, that we have seen is molecular uh, metal organic uh, chemical vapor deposition, MOCVD, or any of the other MBE, molecular beam epitaxy. We can realize this kind of graded junction. Okay, by changing the concentration of the aluminum precursor and gallium precursors. Okay, by the changing the flow rate, by changing the temperature, we can tune the grading of this region. So how this conduction band, this will go like this conduction band, or this will go like this. So there are different type there are different slopes of this. So this slope will the define the field, electric field at in this region. Okay, this electric field will be defined by the composition, by the gradual change in the composition of the material. Okay, so and another thing is, so one beautiful thing of this graded junction is this. Okay, so if there is an electron at this junction, in this region, okay, so that will go downhill. If an hole at this junction, that will go uphill in this region, because holes will move up and electrons will feel electric field in this direction. So they will, both electron and holes are moving in this direction. Okay, so electric field up, which is applicable to that electron, if it is moving this direction, electric field is in this direction. Okay, for this electron, electric field is in this direction. This is the electric field in this direction. This is the electric field in this direction. So there is an opposing field in a single semiconductor. Okay, this at this graded junction, there is this two fields which are acting on electron and holes. Okay, holes are moving this side, electrons are moving this side, the field is opposite. Okay, this cannot be realized in any of the elementary semiconductors. Okay, and these two, this delta ec and delta ev, these things can be tuned according to the materials. Okay, this is more over the materials. Okay, these can be tuned, this delta ev can be tuned, so that we can block the holes, and we can just realize the movement of the electrons. We can block the electrons and we can realize the holes only. Okay, so according to the applications, we can tune these things. Okay, so now what we can see is another thing is, the field is given by, f is equal to f of x at any point x is given by d of ecx by dx. Okay, so d of ecx is, or d of ev, because both uh, and field for this is for the electrons. Okay, and fx also equal to d of ev by dx. Okay, so So the slopes are both the slopes are different for this. Okay, so the electric field will also be different in this case. Okay, that's why. And now another thing I wanted to tell is, huh, this that I already told once, but this electric field, this the electric field can be exponentially, can be constant, or can be anything. Okay, this electric field in this region can be constant also, can be zero also. If if we make this junction such that there is no field, okay, delta ev is equal to 0, we can make such kind of junction also. Okay, so there is no field for the holes, okay, but there is field for the electrons, we can make such type of junctions. So therefore, so and that can be exponential also, that can be constant also. Okay, that constant electric field is there homo homo junctions or metal semiconductor junctions that we have seen. Not the constant electric field, but there is a linear electric field that can be, this can be linear also. Okay, if this is this the dependence is parabolic, this is parabolic, then the electric field will be linear only. Okay, because that is the nothing but the differentiation of this conduction band, the energy of the conduction band. Okay, if this is parabolic, then the electric field will be linear. Okay, and if the this is 0, there is no field in this region because the conduction band and valency band are flat. Okay, so and there is no electric field in this region as well, as both these are flat. Okay, and now, okay, now what we another thing we can see is, okay, there are this is the, okay, there are, there are, okay, HEMTs, okay, MOSFET, that we have already seen, metal oxide semiconductor field effect transistors. And now HEMT, high electron mobility transistors. High electron mobility transistors are too fast, so that's why they are replacing the MOSFETs. Okay, these are gaining the uh, these are nowadays, HEMTs are gaining the, in the field of transistors. What is MOSFET we have seen, which is the silicon based metal oxide semiconductor field effect transistor. So this is a we say, we can say p type semiconductor. This is a p type semiconductor substrate. So what we can do is we grow the oxide, and there is, this is gate, this is source, this is drain, this is n plus plus and p plus plus. Okay, so there is a formation of the channel when we apply the voltage at the gate. When we apply, or how the channel forms when we apply a negative voltage at this junction. Okay, at this junction, so charges are accumulated, bands are bent such that the charges are accumulated, because the, as we apply a negative voltage, these positive holes are attracted towards the junction, the holes will be attracted towards the junction. Okay, so there will be a holes, accumulation of holes, because of, we call it accumulation because this is a p type substrate. Okay, accumulation we call when there is a more charges are accumulated because uh, uh, of the majority charges are accumulated actually. Okay, there are majority charges, p type substrate, so holes are majority. So holes are majority and they are attracted towards here at this junction, so we call it accumulation. If in the next case, when we apply a negative voltage, so there will be a depletion of the charges, so holes will move away from the junction. Okay, so these holes will move away from the junction. Okay, as we apply more and more negative, more and more positive at this junction, more and more positive at this junction, so electrons are, so there will be an inversion of the charges. Electrons will be there, inversion we call, because it was a p type substrate and it is now n type at this junction. Okay, so we call it inversion. Okay, not accumulation. Accumulation happens when there is a majority carriers. Inversion happens when there is minority carriers. Okay, so there is a channel created at this junction, at the interface of the oxide and the semiconductor. Okay, so in between these two, so now when we apply a bias at the source and drain, in between source and drain, when there is sufficient application of the gate bias. Okay, so there is a conduction of these electrons. Okay, when we connect it to the external circuit. Okay, so now so these charges are created when we apply a gate bias. Okay, this we call it enhancement type. Enhancement type transistor. Okay, enhancement mode or enhancement type. Okay, so when there is an inversion, so this there are impurities also. This p type substrate, when we p type is when we dope it with boron. Okay, when we dope it boron or arsenic. Okay, aluminum, boron, gallium. Okay, but we mostly dope it boron because it is smaller in size. So okay, so when we dope it with boron. Okay, so it is when there are holes. Okay, so after, so these impurities will always be there in this semiconductor, in this substrate. Okay, these impurities. So when there is a transportation of charge through this at the interface, after the application of sufficient bias, there will be impurities also. They will scatter these electrons because of the impurities, boron impurities. They will scatter the electrons, so they will decrease the mobility of the electrons here in this junction because of the impurities at the same junction. Okay, so mobility of the electrons will be lesser in this case. But in the HEMT, what happens at the heterojunction, these charge carriers, we can say it electron gas also. This electron gas is separated from the impurities. Okay, so they are not scattered by the impurities. So because of that only, in HEMT, this electron mobility are much higher. These are 5,000 6,000 5,000 6,000 centimeters per volt per second. Okay, so this is a structure of the HEMT. So what is there is, so this is the semiconductor, insulating semiconductor. This is gallium arsenide. Because of gallium arsenide only we can grow epitaxially. So that's why we take gallium arsenide, the substrates, such substrates only. Okay, over which we can grow the material. So undoped gallium arsenide. Okay, so okay, this is the undoped gallium arsenide, which is a buffer layer to, and this is n type, n plus plus, highly doped, which is graded actually, which is gradually doped aluminum gallium arsenide, n type aluminum gallium arsenide, which is graded. Okay, this is the graded aluminum gallium arsenide. Okay, now and there is, in between there is a spacer layer, which is undoped gallium arsenide, undoped aluminum gallium arsenide, which is undoped. This is the undoped region. Okay, and okay, this is highly doped gallium arsenide, P-N type, and this is highly doped to take the contacts from the as source and drain. So there will be very less contact resistance. So that's why these are highly doped. Okay, these are highly doped. Okay, these regions, so that the contact resistance should be as least as possible. Okay, so when we apply, when so there is a, okay, uh, this this junction is heterojunction. Okay, gallium arsenide and aluminum gallium arsenide, that we have already seen. This is the heterojunction. This is the heterojunction. Okay, so this junction is this one. Okay, the Venn diagram of this junction. Okay, so as you can see, there is already an electron gas, electron, the conduction band is is lower than the Fermi level at this point. Okay, so there are plenty of electrons at this junction. Okay, so there are plenty of electrons at this junction already there at equilibrium. This is at equilibrium. Whenever we apply a potential in between source and drain, there will be a current. Okay, without application at the gate. So to turn off this device, we need to apply the voltage. So in this case, in MOSFET, what was that? So to apply, to turn on the device, we need to apply the voltage. And in HEMT, in this case, we need to apply the voltage to turn off the device. Okay, so we can call it a what we can call it a, a depletion mode uh, transistor. Okay, this is the depletion mode. The charges are already depleted. Okay, it is already depleted, and there is an already an inversion. Okay, there is already an electron gas at this junction. Okay, so, and also this was an undoped gallium arsenide. Okay, so if we dope it with N type, so it will be more. So the current will be more because there will be more charge carriers in that case. Okay, so that's why we have this is N type doped. So electrons in this region will move in this region to for the electron gas. Okay, so there will be more very more and more electrons at this junction. And so this, and another thing, one more thing is, so this junction is Schottky barrier. Okay, so there should not be flow of current through gate, so that will be a leakage current. So there, this is a Schottky barrier. This is an ohmic contact, this is an ohmic contact, but this is a Schottky barrier, so that there will be least current flowing through this terminal. Okay, and another thing is, okay, now, hmm, okay, this is a spacer layer which is undoped aluminum gallium arsenide, and this is a graded at, and electrons are more at this point. Okay, so that electrons can move easily in this direction to contribute for the flow of the charges when we apply the bias at in between the source and drain. Okay, now, huh. Now there is another type of transistor which is MESFET. Okay, metal semiconductor field effect transistor. Okay, so in this type of transistor, what happens is this is kind of N type silicon also, whatever type, can be any type of substrate. Okay, this is N type or P type. So whenever we apply a voltage in between source and drain, we are applying a voltage. Okay, we are applying a voltage. So there will be, because of majority charge carriers, there will be flow of electrons. Okay, there will be a flow of electrons. The majority charge carriers will flow when we apply a potential. Okay, but now this is also a enhancement. This is also what say okay, what we call that depletion mode transition. Okay, depletion mode. Okay, now, so now we need to apply to deplete the charges in this junction. So this this depletion, this is very thin. This layer, this N type material is very thin. Okay, this N type, this can be N type or this can be P type. Okay, so now if we apply the voltage at this junction, so this is a Schottky barrier. Okay, so when we apply the voltage, there should not be a flow of current through this junction. So when we apply a voltage, like say negative voltage at this junction, so there will be a depletion of the charges at this junction, at in this region. in this region. So this is an equilibrium when we haven't applied any voltage at the gate, so there will be some depletion because of the Fermi level alignment. Okay, because of the Fermi level alignment there will be some depletion region. So when we apply negative voltage, more and more negative voltage, so this is a kind of, this is a uh, reverse biasing we are doing. Okay, we are doing a reverse bias at in between these two. We are applying a reverse bias. So when we apply a reverse bias, what happens is, so this depletion region width increases. So this is what it is happening here. So it is depleting the charges in this region. So it is, this is the pinch off of the channel. This was the channel, this was the channel. Okay, this was the channel, this was the channel. Now after applying the negative voltage at this junction, so it is, there is pinch off of the channel. Okay, there is no the current flow through the in between the source and drain. Okay, so this is not a compound semiconductor, but this can be done with the silicon also. Okay, but this is a different type of device, which is metal semiconductor field effect transistor. Okay, now this is kind of same as the MOSFET only, but here the junction is, there is no oxide. Okay, but the this junction should be, that must be this Schottky barrier kind of. No, if there is, that is the ohmic contact, there won't be any this effect cannot be seen. Okay, so that should be there. I think this is the end of the slides. So if you have any doubts in this case, you can ask me. So another thing is, that is done. If anyone of you have any doubt, ask me, so I can tell you. So now this is 2D, there are some things. Okay, now in this one I have shown you the examples of type 1 heterojunction only. There are if you can understand the how the bending happens at the interface, you can make any type of the heterojunction. Okay, if whether it is graded junction, whether it is type 1, type 2 or type 3. Okay, whatever it is, however it is, you can make any type of the junctions. Okay, so now, so this was a epitaxial growth. So this is a layer by layer growth. And one another thing is also there, which is atomic layer deposition. Atomic layer deposition is different thing, but that is used for oxide growths. Okay, so we can grow aluminum oxide Al2O3 and ZnO with ALD, atomic layer deposition. Aluminum oxide, indium oxide, zinc oxide, mainly metal oxides are deposited using atomic layer deposition. So that also happens with the layer by layer deposition, layer by layer growth. But in that one, in atomic layer deposition, okay, in MOCVD or CVD works on the principle when both the gases, both the precursor are allowed to allowed at the same time. Okay, so but in atomic layer deposition, the precursors are allowed periodically. Okay, so if trimethyl aluminum indium is going, one is precursor 1 and precursor 2. Precursor 2 is nothing but the oxidant, which can be ozone or water. Okay, which oxidizes this trimethyl indium at the surface to make it indium oxide, In2O3. Okay, this indium oxide can be grown using atomic layer deposition. So they have different applications. Sometimes we can deposit when that is a kind of conformal growth. Okay, this is also a conformal growth. this because this is an epitaxial growth, the layer by layer deposition is there. And if you have some cavities like this, these so when you want to deposit a material completely conformally means it will follow the same structure below this. Okay, so this layer will be grown using atomic layer deposition or chemical vapor deposition. Sometimes you want to etch a layer. This is like SiO2. Okay, you want to etch a layer of this one. So you sometimes uh, with liquid cannot go inside this cavity because of some constraints, because of the surface energies. So but the gaseous molecules can go, that can etch conformally. So that can be done. Okay, so now we can stop here. If you have doubts, you can ask me, or you can leave.